Make sure.
I got it wrong.
All right, so here's the problem, right? And you're asked to find dy dx, which means you have to use implicit differentiation. How do I know that this problem is implicit differentiation? You can't solve it for y. Not easily. You might be able to, but I don't think easily you can solve for y, right? So we can just leave this alone, right? And we take the derivative on both sides of the equation with respect to what variable? X. So I'm going to take the derivative on the left side with respect to x. And then I'm going to take the derivative on the right side with respect to x. And how important is it that I know what variable I'm treating as the independent variable? Is that a big deal, little deal? It's a big deal, right? Because anytime we take the derivative of x with respect to x, we get 1. But if we take derivative with anything else with respect to x, we get d whatever it is dx. So, all right, so we start off over here. We have addition, right, between these two. So I can take derivative of each one separately. So derivative of x squared with respect to x, this is going to be just like our, before we started talking about implicit differentiation, that's just going to be 2x, right? So 2x, and then plus. Now here, when we take derivative, we have a product, don't we? We have a product happening right between those two. So you need to use the product rule, right? So I'm going to do derivative of this times this plus the derivative of this times this. So what is the derivative of 4x with respect to x? Just 4. So I'm just going to put 4. And then times the second function, y squared, right? And then plus, I'm doing product rule, right? Plus, now the derivative of y cubed. 3y squared. And then times the derivative of the base, which is y, with respect to x. So there's my dy dx, right? That's where it's going to appear. I told you, if you're looking for this, then when you take the derivative, it should appear somewhere, shouldn't it? Okay, now I'm not quite done with the product rule, right? I did derivative of this times this plus derivative of that times 4x. And now I'm done with the derivative on the left side, right? Okay, equals now the derivative of y with respect to x. dy dx. So it appears again, doesn't it? It appears a second time. So now what we need to do is get all of our dy dx's on one side of the equation. Anything that does not have dy dx, we take to the other side of the equation. So it doesn't matter which side you go to, right? It's totally up to you. Also, since this is all multiplication, I can put this 4x out here with that 3y squared, make it a 12xy squared. All right, so let me do this. 2x plus 4y squared, or cubed, plus 12xy squared dy dx equals dy dx. So I just put those together. Now let's move this to this side. How many of you who did this correct up to this point moved the dy dx's to the right? And then everyone else did to the left? Okay, so it doesn't matter. I'm going to go to the right here. So I'm going to move this term over here. It becomes negative, right? So minus 12xy squared. When I say move it, what did I really do? I subtracted it, right? So it's gone here. All right, now that I'm here, what's the whole point of getting these together? Factor out dy dx. So the left or right side is dy dx. And when I pull that out, be careful here. When you pull dy dx out of here, what do you get? 1. Minus, and over here, you're just left with the 12xy squared, right? And on this side, the only thing that we had left was 2x plus 4y cubed. And then the last step would be to take this and divide it on both sides. So when I divide this over here on this side, it goes away. And when I divide it on this side, I get 1 minus 12xy squared. So there it is. That's it. Yes?
With the, like the first step, when we take 3y squared times dy over dx.
Yes.
4x. Where does the dy dx, how does that come there?
Okay, so the question here is why does the derivative of y cubed become 3y squared dy dx, right? So can someone want to volunteer to help explain this? Go ahead. The question is, why is it that when we take the derivative of this with respect to x, why does it become 3y squared dy dx? Chain rule. Okay, so the first thing we're doing is we're looking at, like, again, go back to the chain rule. Like, if we have my hand to the third power, what's the derivative of my hand to the third power? It's going to be 3 times my hand squared, right? That would be the chain rule. But chain rule then says you now need to take derivative of this. And when you take derivative of y with respect to x, you don't get 1. You get dy dx. So that's where it comes from, dy dx. Compare that to this, d dx of x cubed. The difference here is we still do the same thing. My hand cubed, the derivative would be 3x squared, right? But then times, we take derivative of this, right? And the derivative of x with respect to x is 1. And so we don't need to write this because it's really a 1. And I'm glad you asked that, David, because that's the main idea from last class right there. You have to understand where that dy dx is coming from. That makes sense?
Yes, sir.
Okay.
Thank you.
All right. Any other questions? So remember from last class, hopefully you can remember this, that the whole idea here is that if we have an implicit equations, right? If we have an implicit equation, then when we graph these, when you graph an implicit equation, it doesn't have to satisfy being a function, right? It can be some picture where it does not pass the vertical line test. So the idea was that, I don't know, it's going to look like something. Maybe it looks like that. But if you can find dy dx, then that means you should be able to go to any point on that curve and still find the slope of the tangent line, so long as someone provides you not just x, but x and y of the point. So let's do an example like that. I'm going to give you an implicit equation, and then what we're going to actually do is find the equation of that tangent line. Not the slope, the equation of it. We've done this before, but we're just doing it with an implicit equation instead. So I was going to pull one of these out of the book. There we go. Oh, this one looks fun. Okay, how about this one? X to the 2/3 plus y to the 2/3 equals 4. And the point that we're looking at is the point -3 root 3, comma 1. And we want to find the equation of the tangent line. All right, so the book actually goes through and draws you this implicit curve. And the implicit curve looks like this. Of course, I would not expect that you know this, but just as a reference. That's kind of what it looks like. And this is actually called an asteroid, according to the book. We call this an asteroid, all right? And we are, guys, I can hear you, means everyone can hear you, all right? Okay, so we go to a point, let's see, negative 3 root 3, 1 would be somewhere over here in the second quadrant, right? Negative x coordinate, positive y coordinate. Somewhere over here, we're trying to find the equation of that tangent line. All right, so what we need to find the equation of any line is that formula, right? Right there. That's the equation of any line, as long as we have the slope and the point. We already have a point, don't we? The point's given right there. So we have x1 and y1. All we need is the slope of the line, but the slope of that line is actually going to be the derivative of that, right? It's going to be the derivative of that at that point right there. Understand? So let's go find the derivative. So we're going to have to do implicit differentiation here. Well, we don't have to, but let's do it. So if I do implicit differentiation, I'm going to take the derivative with respect to x of the left side. And derivative of the right side with respect to x. All right, so I can do these individually because there's addition. So what is the derivative of x to the 2/3 with respect to x? 2/3 x raised to the negative 1/3. And that's just your power rule, right? Power comes out, subtract 1. And remember here, that I just talked about this. The reason why we don't put anything after this is because when we take derivative of x, the base, right, it's just 1. Okay, now plus. Now we do the same thing here, right? So we're going to get 2/3 y to the negative 1/3. But what's the important piece that goes after that? dy dx. Okay, so times dy dx. And then equals 0 because, well, the derivative of a constant will always be 0. Always, always. That's never going to change no matter which calculus class you ever take. The derivative of a constant is always 0. All right? All right. So now, like on a quiz at this point, I would probably ask you to solve for dy dx, right? Like you did just now. But when you're asked to find the equation of the tangent line, do y'all agree that all we really need is to know what this is, right? We need to know this, right? I could go try and solve for this, but instead, why don't I just use this point right now? This is my x-coordinate, right? This is my y-coordinate. Let's just plug this in for x and this in for y over there and see what we get, all right? I'm not even going to simplify that. So if we plug this in, we're going to have 2/3. And then we're going to have, what's x for us? Negative 3 root 3 raised to what power? Negative 1/3. Okay, plus 2/3. And then what? 1 raised to the negative 1/3 times dy dx equals 0, right? So all I'm doing is plugging things in here. Any questions? All right, one of these is easy. This one right here. What is 1 raised to any power? 1 raised to any power. Just 1, right? It's just 1. So this doesn't require any simplification. That's just 1. This one I'm going to rewrite a little bit. And I guess I'll do it right here. That one over here I'm going to write as this. 2 over 3 cube root of negative 3 root 3. And then plus 2/3 equals 0. So let's just make sure you understand that. Right? Negative power means drop to the bottom. Negative power means drop to the bottom. So it's going to join the 3 that's down here. And then 1/3 really means cube root. So that's just me rewriting this with radicals instead. And then we said, oh, I'm missing something, aren't I? Missing dy dx, sorry. Equals 0. So we said that this is 1. So 2/3 times 1 times dy dx is that. And now at this point, let's try and figure out what dy dx is. All right, so notice that everything else is a number. They're ugly numbers. Do you agree? Okay, so what I'm going to do to solve for this is first I'm going to bring this whole thing to the other side, which makes it negative. Ugh. Y'all agree with that? Yeah, I'm going to multiply both sides by 3 over 2 to clear this fraction. So I multiply top by 3, bottom by 2. So when I do that, it goes away over here. So on the left side, I have what? Just dy dx, right? Left side is just dy dx. And I multiply both sides by 3 halves, right? I guess I can show it. 3 over 2, 3 over 2, right? Gone, 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 gone. And over here, gone, 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 but with a -1 up there, right? That's going to become -1. So my right side should be -1 over what? Cube root of -3 square root of 3, right? Is it possible to take a cube root of a negative number? Yes. Yes, you just can't do a square root. So that's it right there, right? That is the slope of the tangent line at that point. So we're just going to plug it into this formula and we'll be done. It's going to look ugly. It's going to look ugly, but it's what it is. I'm not going to get the decimal. I'm not going to get on my calculator and get that as a decimal. I'm just going to give the exact answer. So the equation of the tangent line looks like this. Y minus, what's y1? 1, right? So y minus 1 equals m, which is the slope of the tangent line at that point, which is this. -1 over the cube root of -3 square roots of 3. And then in parentheses, x take away what? That, right? So it's really plus 3 root 3. That is the equation. Let's check. So what I'm going to do is I'm going to ask the computer to graph this. I'm not sure how this is going to go, okay? No promises here. Leave. Okay, we had x raised to the 2/3. That's all messed up. There we go. Plus y raised to the 2/3 equals, what was it, 4? Hey, not bad, not bad, not bad. Okay, so there's our asteroid. And now I'm going to type in the equation of the line we just came up with. So I'm y minus 1 equals, the slope was -1 over, okay, the way I'm going to do this is this. I'm going to go -3 times the square root of 3, but then I'm going to take all of that and raise it to the 1/3. Y'all can't even see that very well, at least. Right? So this is y minus 1. Where's my negative? Oh, -1 over -3 times root 3, all raised to the 1/3, which is cube root. And then I still need this part right here. And so what I should see when I finish this up is a line passing through that point tangent to that asteroid. X plus 3 times the square root of 3. How do I do points? Let me just try something. Oh, it does points easy. Oh, nice. I like that. Okay, so what was the point? -3 square root 3, comma 1. There we go. Yes? We pass through that point, and we sure do appear to be tangent, don't we? Okay. All right. That was a little messy, but it's messy because of the numbers, right? The derivative was pretty clean. Would you all agree? Like the actual implicit differentiation, not too bad? All right, I want to show you another example. It's kind of a strange example, but I think it shows something interesting about this implicit differentiation. So let's go back and let's look at this right here. If I ask you to find y prime, that really means dy dx, right? I told you all that last class. Y prime, the y prime we were finding before we did implicit, really meant dy dx. So let's do this the way that we would have done it before implicit differentiation. We would have said, okay, y equals, let's see, take the derivative of this. That's the same as x to what power? -1. And then we can use the power rule in that, can't we? Yeah, I realize you could do the quotient rule, but you're wasting your time. Just convert it to this and do power rule. All right, so what would the derivative of that be according to what we learned way back when? -1, x to the -2, which is really -1 over x squared. Just drop that x to -2 back down. Good? Yes? Okay, now, I want us to take a look at this problem again. But this time, before we do any derivatives, I want to multiply both sides by x. So if I multiply both sides by x, I get that, right? Yes? Okay. Now, let's take the derivative of this implicitly. That means take the derivative with respect to x on the left side, and then equals the derivative with respect to x on the right side. If we do this, we're going to find dy dx, aren't we? Should we get the same answer?
Yes.
We better, right? We better. Okay, so let's try it. The derivative of this is a product, yes? Okay, so we take first the derivative of x with respect to x, which is 1 times y, plus the derivative of y with respect to x, which is dy dx, times x. Okay, so that finishes product rule on the left, equals 0. Okay, let's solve for dy dx now. So if I try and isolate dy dx, I'm going to move this guy over. So I get dy dx times x equals -y, right? And now let's divide both sides by what? X, and you get -y over x, right? So here's the answer doing it with implicit differentiation. Here's the answer not with implicit differentiation. I said the answers should match. Do they match? They don't necessarily look like they match. I saw you shake your head yes. No? Yes? Yes? You said they match? How? Okay, it's okay if you were just nodding to nod. I just wondered, maybe you saw it. That's why I was going to give you an opportunity to kind of show off a little bit. No?
Y equals x.
What's that?
Y equal 1.
Yeah, so go back over here, right? Look at this right here. What did we say y was? Y is 1 over x, right? So let's take this answer and let's replace y with what it is. That's 1 over x, right? Over x. That's 1 over x over x. And so now if you write that as a fraction over a fraction, you're going to multiply by the reciprocal, right? And what do you get? -1 over x squared. See? They are the same answer. It's just this one said, hey, if you want me to find the slope of tangent line, you better give me the y and the x value. This one said, all you have to do is give me the x value, right? But it turns out because we know a relationship between y and x, we could go back here and replace that y with that relationship, and then it's all good, right? So this step right here, I replaced this y with that up there, right? And that's how I got to here. In general, we can't do this because we already know that when we use implicit differentiation, we like to do it on problems where we cannot solve for y, right? If we can solve for y, we like the old way. But if we can't, then we want to use implicit. So this step of switching from here to here really in general won't work unless we can solve for y. But again, if we can do that, then we do this. So I'm just showing you get the same answer, that even though it's a different sort of method, the math is all consistent. And that's what we always want in math, right? Everything to be consistent. You don't want two different engineers working on a problem getting two different answers and they're both right. You don't want that, right? Okay. How about this one? What am I asking for? The second derivative. So way back when we were talking about derivatives, said there's different notations. And the notation we started with was y prime, then we did like y double prime, and we said if you go high, like if you want to do higher derivatives, you could replace it with a number and put it in parentheses. But I said there was a different notation, the Leibniz notation. And with the Leibniz notation, here's how we represent second derivative. And then 3 there would be third derivative, and so on and so forth. So let's try and find the second derivative of this equation. All right? Okay, so to do this, what we're going to do is first find the first derivative. All right? So let's try and take the derivative first with respect to x of square root of x plus square root of y equals derivative with respect to x of 1. All right, here are my little sticks over here. These things look lonely over here. Luke? Okay, Luke. Taking the derivative with respect to x of this, we have a sum, right? So I'll let you start with the first one. What's the derivative of the square root of x with respect to x? Almost there. Yep, okay, 1 over 2 root x. And that was one of them that I asked you to just burn in, right? Burn that in. Okay, so we don't need to worry about any chain rule here, right, Luke? Because we're taking derivative with respect to x, so we're done. Okay, plus, Luke, I'll let you keep going. Derivative of the square root of y this time. Okay, so what do you get first? You're going to get a dy dx, but what goes before that, though? You still have to take care of the derivative of the square root. There you go, 1 over 2 square root of y. But the additional part to this is you're going to have dy dx attached to this. And that's, again, because after you get finished taking the derivative of the square root of my fist, you have to take derivative of my fist with respect to x, which is this. Is that clear to everyone? Okay. And then Luke, you can do the right side for us. 0. Okay. So Luke just did the derivative, right? Everyone good? Now, what we could do at this point is go solve for this, right? Yes? We could go do that, but that's not what I'm going to do. What I'm going to do is, at this point, I'm going to take the derivative again, the same way I just did, on both sides with respect to x. Okay, so let's just follow me through. This is the first time I've ever shown this. I'm going to take the derivative with respect to x a second time. Now on this one, I'm going to rewrite this one, okay? I'm going to rewrite it as 1/2 x to the negative 1/2, and over here plus 1/2 y to the negative 1/2 times dy dx, and then equals derivative with respect to x of 0. Okay, so all I did was rewrote this root as 1/2 power, then brought it back up. This root is 1/2 power, brought it back up. And the reason I did that is because I know I'm about to take the derivative again, and it's easier for me to work with the power rule this way, right? Okay. Any questions on that step? Some of these are blank. James.
Yes.
I'm going to turn, you put a sad face on here. First time you ever filled this out?
Did I put a sad
You put a sad face.
I'm going to put a happy face.
I'm going to make it happy now because you are happy. You're not sad. Okay.
Can you get me angry yet?
I'm going to put you a little cigarette in there. Okay. So you're just chilling. There you go. All right, so you ready for this derivative? All right, so we're taking the derivative with respect to x of this thing. Okay, so what is that? Negative 1/4 x to the minus 3/2. Okay, so you're taking 1 away from a half, negative half. And do we have anything else coming out of this? That's it, right? You want to keep going?
Yeah.
Okay. So I'm not going to put the plus yet because I think you're about to tell me to put something else. So what's...
Well, it's going to be a negative.
Oh, wait, hold on, James. I almost led you down the wrong road here. James, you have to take derivative of this now, right? Does everyone see that? Does everyone see this? What is that? That's a product, isn't it? See, we didn't have a product over here. We had a constant in front of the function, so the constant came for the ride, it just came out. But here we actually have a product, and that means we have to do the product rule. Okay? No way around it. Okay, so now, continuing, I will put plus, and because it's a product rule, I know I'm going to get several things here, right? So I'm going to just put it in parentheses. So it's going to be derivative of this times this plus derivative of this times this, yes? Okay, what's the derivative of this? Negative 1/4 y to the negative 3 halves. Does everyone agree with him so far? Keep going. Now, where's that dy dx coming from?
I think it's going to come from the first one.
From the first one, exactly. Look, when he's taking derivative of this, right, with respect to x. So first he does the power rule, that's here, but he then has to take derivative of the base, which is dy dx, right? Yes? But then times what, James? dy dx again. Okay, I need anyone that right now just got nauseous from this, let me know. We can go make sure this makes sense, yes?
Does it make sense?
Okay, so derivative of that piece, we're doing product rule. Derivative of this times this plus derivative of this times this. Okay, derivative of this first is that comes out, right? And then we subtract 1 from there, we get that. But then we have to go take derivative of the base, chain rule. Okay, so the derivative of the base here would be dy dx. So that's where this one comes from. But then the product rule says after we're done with this derivative, we then need to multiply times that. So that gives us a second factor. So if this is f and this is g, this right here is f prime and this right here is g. And now I'm going to continue with the product rule, g prime times f. Right, that's what I'm doing. Wait, Elijah? What's this part? So what do I need here first? Okay, so plus though, right? Plus, okay, and you're taking the derivative. You need to take the derivative of what? Of the derivative, which is the second derivative, right? It's the second derivative. You're taking the derivative of the derivative. So this right here into the product rule becomes d2y over dx squared, like that. And look, weren't we trying to find that? So it's got to come out somewhere in the problem. It's got to show up, right? And now it just showed up. Okay, understand?
Yes.
Okay, now we're not done because that's that times, yeah, this thing, 1/2 y to the negative 1/2. Are we done with the product rule? Yes. Close it off. And then we can go to the other side. Equals, what is the derivative of 0? Still 0. Okay, good. Quite a mess there, yes? Would you agree that's quite the mess? So now what I'll do is this. I'm going to write negative 1/4, just to kind of clean it all up. X to negative 2/3. This plus is going to become a minus because I'm going to just get rid of the parentheses. It's going to become minus 1/4 y to the negative 2/3, 3/2, sorry. I flipped this, didn't I? Sorry about that. That was supposed to be 3/2. And then we have, what is dy dx times dy dx? That's dy dx squared. That is not this. This is the second derivative of y with respect to x. This is the first derivative of y with respect to x squared. So the way I'm going to write it is this. Right? Okay, that's this, and then I have this piece plus, let me erase that one, plus, now there's my second derivative, and then times 1/2. Crap, I'm going to run out of room because I don't want to erase this. I don't want to erase that. But, okay, so instead of erasing that, can y'all just like agree with me on this? Back here on this first derivative, do y'all agree that that would be this? That's that. So I just move that piece over there to this side. And then I'm going to multiply both sides by 2 root y. So 2 root y here is going to cancel. 2 root y here, it's going to go on top. So I'm going to have dy dx equals negative 2 root y over 2 root x, which is really just negative root y over x. So the 2's canceled, and since these are both in a root, I can just put them all together in one root. So that's what dy dx is, right? Okay. Now finish this off. That, and then I still have this. 1/2 y to the negative 1/2 equals 0. Yes?
Wouldn't it be negative second derivative times half?
Negative? Where, here?
Oh wait, no, never mind. My bad. Sorry, I thought with the negative 1/4 side. Sorry, I messed it up.
You're good, you're good. All right, y'all there still? Okay, now the reason why I went and did this step, does anyone see why I went and solved for dy dx? Because I can take that answer and plug it in right here, right? Not here, but right there. And then I can square it. And so what would happen if you square this? You just get y over x. The negative goes away. So now I'm really going to start trying to clean this up. Watch me, watch me. I've got negative 1 over 4 x root x. Okay, so what happened there? Drop this down, right? Drop this down. It becomes x to the 3/2. But that means x cubed square root, right? X to the 3/2 means the square root of x cubed. So you can take out one group of 2 comes out, and it leaves 1 in there. I'm going to try and do the same thing on this one. So this one will become minus 1 over 4 what? Y, square root y. But then what am I multiplying that times? Y over x, that piece right there. So I'm going to say times y over x. And then plus, it got squared, right? So yeah, this is the first derivative squared, so we have to square this side and square this side, so the negative is going to go away. So we still have here now the second derivative times 1 over 2 root y equals 0. Isn't that pretty? Very pretty, very pretty. All right. Just trying to decide what I want to do here. I want to try and get this by itself, right? Because we were supposed to solve for that. We're supposed to solve for that. So there's different things we can do here. I could leave this here and move all of this to the other side. Do y'all want me to do that? I could do that, right? That's a legal move. Let me do that. Okay, so d second derivative times 1 over 2 root y equals, all that stuff moved over, so it becomes positive on both, right? Positive 1 over 4x root x plus 1 over 4y root y times y over x. All right, so I've moved those things over. What can I do next?
Y over x
Say again?
Even the y over x was the,
Oh, like this can cancel? I'm sorry. Is that what you're saying? Like that y and that y can cancel?
Yeah.
We could do that. I don't mind doing that. So this and this are gone. All right. I'm trying to get that left side to just be the second derivative. So how can I get that second derivative by itself? Multiply both sides by 2 root y. Let's do that. So I'm going to multiply this side by 2 root y. Right? On this side, it's going to go through here. And then this has 2 terms. So I'm going to multiply this side by 2 root y. Right? And that will have to distribute to both of these. I realize this is messy, which is part of the reason I do it on camera, because then you can always go back and watch it if you need to. All right, left side, they cancel, right? So now we finally have the second derivative isolated. Equals, now when we distribute this thing over to this, what are we left with? Root y over 2 x root x. All right, that's what happens there. The 2 and the 4 reduce, okay? All right, now when we do this over to this one, the root y's are going to go away, aren't they? The root y's are going to go away. So all we're going to have is on top what? It's going to be plus 1 on top. And on the bottom, the 4 and the 2 reduce, so we have a 2 and this x. Yeah? We're there, okay? We're there. You could argue that's the derivative, but that's not the back of the book answer. Okay, so watch. Check this out. We're going to get a common denominator. Put them together, and something kind of cool is going to happen. So what would I need for a common denominator between these two? I need this to have a root x here and a root x on top, right? That's what I would need? Okay, so let's see what we would get then. The second derivative of this should be equal to, all right, they're going to have the same denominator now, aren't they? So the denominator is going to be 2x root x. What's the numerator going to be? Root y plus root x. Yes? That's still not the answer in the back of the book. The answer in the back of the book, I forgot the problem. The answer in the back of the book is this. Whoa, what? Why is that the answer in the back of the book? That was the original equation. What was the original equation we were given that we were differentiating? So this is the original problem, right? Said, okay, this is the relationship we have between x and y. This relationship must always be true. So if we graph it, whatever it is. We found the second derivative, and when we found the second derivative, we found that if we do combine these together, the numerator becomes our original equation, and so we can replace that original equation with 1, right? Because it has to be equal to 1. So after all that algebra, can you somewhat appreciate the challenge here is the algebra? I mean, the derivative was a little tricky, I will admit. That second derivative in there is a little tricky, but getting to the back of the book answer, that's really, It's like, I don't know if you would, like on a test, I don't know if you would get to here and actually know to do this. So I wouldn't necessarily, again, take off if you got to here. But again, if you're trying to match up with the book, I continue to urge you to try and make your answer look like the book's. Whew. All right, that was, well, that's a homework problem, or it's kind of like from the homework set. Yeah, I didn't pick like a hard problem for you. This is where we are. Yep.
I have a question.
Yes. Oh, don't erase.
So, when you took out the x from the square root of
Yes.
x, that didn't turn into x squared.
squared?
No, because we had x to the 3 halves, which is the same as x cubed square root, which is the same as x squared times x under a square root, which is the same as square root of x squared times square root of x, and that's x. The square root of x squared is x. And then you still have root x. So this becomes x root x. So for every group of 2 that you see under a square root, you can pull it out as 1. All right, well, how are y'all feeling? I have an exam in less than 48 hours. What?
That's a hell of a way to put it.
I didn't hear it. I didn't hear what he said.
I said that's a hell of a way to put it.
What I said or what someone
How
responded?
you said it. Like, we have
Less than
an exam
48
in
hours?
48
Yeah.
hours.
Well, I mean, yeah, that's the reality, I guess. Not trying to make it sound worse than it is, because that's what it is, right? So I will talk about the exam here towards the end. I'm just wondering if I should do another example, or if you feel like I've done enough for you here. Do you feel like I've done enough implicit differentiation, or would you like to see something else? Or
Can you do another one of those double prime?
second derivatives? Sure. So this one I'm going to make up, all right? So I'm not going to go from the book. So you know how this problem, we got to the end, and it turned out to be something really, like that thing turned into 1 on the top? That's because they made that problem very special for us so that it would do that. I'm going to make up a problem, so I can almost guarantee you it's not going to do that, all right? So here's the problem. xy squared equals sine of x plus y. Find this. Find the second derivative of this. All right, so here we go. The left side, I need to find the derivative, right? So product rule. Everyone see we got product rule right there. So the derivative of the first one is going to be what? 1 times derivative of this one, or sorry, yeah, times this one, not derivative. And then plus the derivative of this one, which is 2y dy dx times x, right? So that is the product rule of the left side. Equals the derivative of sine of something. Cosine of x plus y, chain rule, times the derivative of what's in here, right? The derivative of what's in there is 1 plus dy dx. In my homework solution videos, for those of you who have watched them on this, in my homework solutions, do I use dy dx or do I use y prime? Use both? I prefer y primes, but I'm trying something. In this class, I'm going to just stick with this. I'm not going to change it. We're just going to stick with it, all right? And it's mostly because of what we're going to do in the next section. All right, now, at this point, right here, you can take the derivative again, okay? Because we've already differentiated, right, one time? So without cleaning anything up, I'm just going to differentiate right here. Okay, so I'm going to put like a squiggly line here. And just so everyone knows, I'm differentiating with respect to x again, all right, on this next line. I just don't want to have to rewrite the whole thing again. Okay, so that one is kind of annoying, so I'm just going to get rid of it. All right, so what is a derivative? I can do these separately, right? Those separately. Oh, sheesh. Wow, that's going to suck. Okay, let's do this. This right here is going to be what? 2y dy dx. Uh-oh. Plus. Do y'all see why I'm not happy about this? You actually have like a triple product rule. Triple product. You have 3, right? And we've never done those in class, but there has been one like that in the homework. So I've got to take derivative of 3 things. I have 3 things being multiplied. So the way that you should approach this is just make a product wherever you want. I don't know. I'll make the product right here. So it's kind of like this is the f and this is the g. Okay? Now I realize g is still a product, right? But I'm going to just follow through with the product rule on this. So what is the derivative of this right here? Right, we're going to do f prime g plus g prime f. So what's the derivative of 2y? 2 dy dx. Right, 2 comes for the ride. The derivative of y with respect to x is dy dx. So that's f prime, yes? Times g, right? Which is dy dx times x. Okay, f prime g, right? F prime g, f prime g. Now we do plus, right? G prime. Oh, crap. What's g prime? What's the derivative of this? Well, it's a product, isn't it? So I've got to do this on the side. I've got dy dx times x, and I'm supposed to take derivative of this right now, right? So let's do a quick little product rule on this. Derivative of that times this plus derivative of this times this. So what's derivative of this with respect to x? Second derivative, y with respect to x, times x, the first one, plus the derivative of x, 1 times that. So just dy dx. That right here is just g prime. And we still have to hit that with f, don't we? The first derivative was much easier than the second derivative, right? The second derivative is turning out to be a nightmare. All right, so I'm going to plug this in. If I ever gave this to you on a test, I would not ask you to simplify. I'd just ask you to take, just take the derivative twice. All right. Let's back up. Derivative of this with respect to x plus the derivative of this product was derivative of that one times that one plus the derivative of this one, which we did over there, which is that, times 2y. That's our g, that's our f. Okay, so that should take care of the left side, shouldn't it? Yeah? That's the left side. Nice, nice. This isn't terrible. Okay, on the right side, we have to take derivative, don't we? And what do we see? Another product right there. Do y'all see that? That's cosine of this times this. So we have to do derivative of this times this plus derivative of this times this. Okay, what is the derivative of cosine of x plus y? Negative sine of x plus y times 1 plus dy. Where is that coming from? Chain rule, right? So that has nothing to do with this. That has to do with when you take derivative cosine of something, you get negative sine of that something times the derivative of what's inside, which turns out to be this. Okay, so this right here is the derivative of this first one. Then I say times what? This right here. plus, you feeling a little overwhelmed? So this is like our new F and our new G. This right here is F prime times this one is G. And then we do plus, what's G prime? So what's the derivative of this with respect to X? Yeah, just the second derivative. Right? Because the derivative of 1 is 0. Are we done? This is G prime, right? G prime, and then finally times F, right? Which is cosine of X plus Y. Yikes. So you asked for another example. Sorry, I don't have a, what am I thinking? I don't have a limiter, I guess, built into myself. I just kind of try something and see how it worked. And this one was pretty ugly. I wouldn't give you that on a test. Maybe as a bonus. Maybe as a bonus. I would never ask you to solve for the second derivative now, right? Like isolate this. That'd be, I mean, is it possible? Sure, but it's just a lot of algebra. So I think if you can follow that, I mean, I think you're in a good place. Like if you can follow everything I did there, then that's good. It's not pretty, but it's very systematic, right? The way you go about it. There's just so much room for error, right? There's just so much room. Oh, I forgot the G on that product rule, So just be real careful with it. All right. So we have a little bit of time. I mean, we have a lot of time. Shouldn't say a little. We have like almost 30 minutes. I just want to see what your feeling is about what I'm about to put up here. Where do I want to start? Yeah. Yeah, someone recognized it. All right. This is known as the ideal gas law from what, chemistry?
Yes.
This is an equation used in chemistry that relates pressure. So let's say you have a container, sealed container. We can measure the volume of this container. We can measure the pressure inside of the container, and we can measure the temperature inside of the container. Then this must always be true in a container full of a gas, all right? The pressure times the volume must always equal N times R times the temperature. And N and R are constants. These don't ever change. These are, well, you're taking chemistry, so.
Forgot exactly what N is. I think N is the mass, and then R is going to be 8.134 times joules per mole.
Something, yeah. So this is like number of moles, or maybe it's the other way. I think this is like Avogadro's number, and then like number of moles, or something like that. Okay, but the idea is that you have an equation, don't you? So you see this. You can actually see this equation in action anytime you take like a soda and open up the soda, right? You'll hear shh, right? You'll hear that. But the air that comes out when you open up a soda is usually a little bit colder than the air around it. And the reason why is because if this is an equation, right? If you open the soda, what happens to the left side of the equation? It gets bigger or smaller? It gets smaller, right? Because pressure, when you open a container, pressure drops, right?